Hello, my name is Zoe and my group partners are Charlie and Oriole. Today we'll be talking about turbo machines from chapter 12. So as an introduction to turbo machines, they're classified as either pumps or turbines. They're mechanical devices consisting of several blades attached to a rotor, so then they can either provide energy to a fluid, which would be a pump, or extract energy from a fluid, which is a turbine. So some examples are a windmill as a turbine, or a boat propeller as a pump. Turbo machines have three classifications. There's axial flow, radial flow, and mixed flow. Over here on the right, case A is a radial flow fan where the fluid flows around the blades. And then an axial flow fan goes in the same direction as the rotor. This is one of our main equations. It's how to find fluid velocity. So V is fluid velocity, W is relative fluid velocity, which would be if you're on the blade watching how the fluid moves, and U is the blade speed. So if you want to find the blade speed, it's the angular velocity times the radial distance. Over here on the right, we have a velocity diagram, and you'll see as fluid enters on the right and then leaves on the left. Entering fluid has no component of absolute velocity in the direction of blade motion. This is seen from V1 only moving in one direction, and then as it exits, it's rotated, so it has both tangential velocity. So the blade is pushing fluid forward as the fluid goes through the rotor. Now we're going to talk about the differences between pumps and turbines. So a turbine's blades move from force of the fluid, meaning the fluid is doing work on the turbine blades. And then a pump moves because of the fluid, so the fluid is acting on the pump's blades. And here's a little problem that you can do. Basically, you need to determine if this is a pump or a turbine. So now we have a couple equations to cover. The one on the left is used in the case of steady flow, and on the left side of that equation is the sum of the external torques on the control volume, and the right side is the net flow rate of angular momentum through the control volume surface. Now on the right, this equation is called the Euler turbo machine equation, and it's used to find shaft torque only in the case of 1D flow through a rotor. The subscript 1 means the inlet flow, and the subscript 2 means the outlet flow. And here are some sign things. So if the V direction is the same as the U direction, then V is positive, and vice versa. And then if the torque direction is the same direction of rotation, then torque is positive. And these signs up here, the negative sign means that it's inlet flow, and the positive sign means outlet flow. So this equation down here has the same sign conventions as the other one, where negative is inlet and positive is outlet. So if you see shaft work as a lowercase w, that is shaft work divided by the flow rate. And then shaft work is positive when power is supplied to the control volumes, and this is true in the case of pumps. So in the case of turbines, it would be negative. On this page, we have a couple equations. So this one refers to the small triangle, which is seen here. And then this one refers to the large triangle, which is the entire right triangle. So then using our formula for shaft work by flow rate from before, I'll write that down here. So we can combine the small equation and the large equation. So using the equations for the small triangle and the large triangle, we combined them to get this equation for V times U. And then we used that equation and the shaft work over flow rate to get this equation at the bottom here.
We're going to be talking about centrifugal pumps, which are one of the most common examples of radial flow turbo machines. So basically how this one works is fluid is sucked in at the center where the eye is shown, and it is pushed radially outwards by these curved impeller vanes or blades. And as the fluid exits radially outwards, it hits the volute casing on the outside, which immediately slows it down and increases the pressure as it moves out through the discharge of the pump. So that's the basic design of a centrifugal pump. They can come in many different classifications. So for one, the impellers can be open or closed. That just refers to whether or not there's a backing on the impeller and it's exposed or closed to the surroundings. The impellers can be single or double suction, which just refers to whether or not fluid is entering at one end or both ends. And double suction just decreases the initial velocity as there's double the area entering the system for the fluid. Pumps can also be single or multi-stage. This just refers to the amount of impellers used, so multi-stage pumps will have several impellers lined up together. And finally, pumps can be a variety of these combinations, so you can have one pump that has many different classifications. To analyze the math of the centrifugal pump, first we needed to define some force vectors. We're going to have the v vector, which is the absolute velocity of the fluid entering. U is going to be the velocity of the blade, denoted by the radius times the angular velocity. And finally, big W is going to be the relative velocity, and this gives us V equals W plus U. Using this formula, we can substitute in and find that the shaft work is going to equal the density times the flow rate, and then you have the outer radius times the outer V vector minus the inner radius times the inner V vector. And then knowing that the shaft power just equals the shaft work times the angular velocity, we can find that the shaft power is going to be a similar formula, just replacing those radii with the u found from the radius times the angular velocity. And then using Bernoulli's equation in kind of morphing these two, we can get an ideal head rise. This is just assuming tangential velocity is non-existent, so it's basically perfectly functional. Obviously, this is not going to be realistic, so we have a non-ideal formula here too that incorporates each velocity component of the blade. The pumps can also be analyzed dimensionlessly so that we can compare two pumps. So we have a number of dimensionless coefficients we use for this. The first being the head rise coefficient. The second is the power coefficient. We have the efficiency, and finally the flow coefficient, which is arguably going to be the most important for us here. Because using the flow coefficient, we can compare two different pumps at different scales as long as they're from the same family. So, as long as they're geometrically similar and similar in function. But using this idea, we can compare each one of these coefficients and predict how pumps will act as you scale them up. So you could perform experiments on a pump that's of a much larger scale and then use these formulas or equations to scale it up and predict the performance of a large scale pump. There is some discrepancy, but for the most part, this is a solid assumption. And finally, we're going to have axial and mixed flow pumps. As opposed to radial flow machines, these systems are going to require high flow rates and low heads. So that means higher specific speeds. And these machines also are going to produce fluid axially, which is parallel to the plane that the turbine is rotating on. So that's the main difference between the radial and axial flow pumps. And the mixed flow pumps are in following the same vein. They just have some component of both radial and axial flow. So it's going to be a combination of a radial and axial machine. And we have this rule of thumb that in general, as you go from radial machines to axial machines, the specific speed is going to get higher, the head is going to decrease, the speed of the system is going to increase, the impeller diameter is going to decrease, and the eye diameter is going to increase as well.
And I'm going to talk about fans, turbines, and compressible flow turbo machines. First of all, fans. They are commonly used to move huge amounts of gases or vapor at a low rate speed, so rotation is pretty slow. They are normally made of cheap metal, and also the density is considered to be constant, so it's considered incompressible flow. They have different names depending on the location of the fan on the system. They're called blowers if they're put at the entrance of the system, exhausters if they're put at the end, and boosters if they're in the middle. They also have radial flow, mixed flow, and axial flow. As you can be seen here, they can go from the small fans that we use to cool down our computer system or desktop, laptop system to huge fans on top of the roofs to move the gas out of the buildings or ventilate them. Then we go to turbo machines. Devices that extract energy from a flowing fluid exert a torque on the rotor in the direction of its rotation. There's two types, impulsive turbine and reaction turbine. Impulsor turbine, the most common one is the Pelton wheel, using tangential flow and is best for lower flow rate and high heat operations. The relative velocity does not change, but the direction and magnitude do, moving the wheel and producing a torque output. The maximum power is obtained when the absolute velocity obtained at the end is half of the one before going through the bucket. The fluid does not cover the entire wheel or all the buckets at the same time. It actually just covers a few of them, making a fluid go through the bottom ones, producing the rotation of it, and that produces the torque. And then there's also the reaction turbines. There's two main types, the Francis turbine that it can be seen on the left, and the Kaplan turbine that it can be seen on the right. The Francis turbine uses radial flow, and the Kaplan turbine uses axial flow. They are best for high flow rate and low heat operations. The angular momentum, pressure, and velocity of the fluid decreases as it flows through the turbine rotor, extracting energy from it. In this case, the fluid fills all the blades, producing work at the same time. The blades are shaped with a certain angle to make more movement by pushing the fluid downwards. As it can be seen, the fluid enters through the channel and it makes the the wheel with the blades spin around, producing a downward motion of the fluid, and that's what makes it the torque and the wheel with the blades rotate. Last but not least, compressible flow turbomachines. In this case, we cannot consider the fluid a incompressible fluid, but instead we have to take into account the change in density in the fluid. There's compressors that are a continuous compression of gas flowing through the device. In this case, the energy is given to the fluid, increasing the pressure, density, and temperature, producing a high heat increase. There's two types: radial flow compressors that are essentially like centrifugal pumps that use gas as the working fluid, and axial flow compressors that has a lower rising pressure than the radial but is good for higher flow rate. It also consists of several stages, with each stage containing a rotor-stator row pair. The compression made by the compressor is given by the total pressure ratio, PR, and is multiplied by the inlet pressure. The gas can also be compressed several times to make it a higher compression, like on the axial flow compressor. To make that, the outlet fluid of the compressor has to be the inlet of the next one, making the overall compression ratio PR to the n being the number of times being compressed. On the left, we can see a axial flow compressor that is the motor of a plane, and that's the compressor stage where it is being compressed several times. And we also have compressible flow turbines. In this case, they remove the energy from the fluid, decreasing the pressure, density, and temperature at the outlet of the compressor. Although axial flow is the most common type, radial have some good uses and advantages. Their main advantages are robust and durable, axial compact, and relatively less inexpensive. Axial flow turbines are widely used compressible flow turbines. In this case, in the right, we can see an example of axial flow turbine, and it has several stages to decompress the fluid. And that's it. Thank you so much for listening, and we hope you enjoyed our presentation.